Hello students, welcome back. Previously, we went through the definition of the homomorphism, either this way or that way, they're equivalent. And then we went through some terminologies associated to homomorphism. Monomorphism, epimorphism, and most importantly, isomorphism. We went through some examples as well. Mostly just easy examples. And then here's one more. Reduction modulo m. Apparently our textbook author thinks this one is maybe a bit harder or maybe a little bit more important. Whatever he must have thought, he separated as something and then named accordingly. But in my opinion, this one's just as trivial. Okay, here we go. Let gamma from z to zn be a natural map. Yeah, really natural, end-to-end bar. Then we have to prove that gamma is a homomorphism. As a matter of fact, this natural map can be rewritten like this using the division algorithm. This n is qm plus r, and then m is 0, congruent to 0 modulo m, so that drops out, and you just get r bar, and r bar is simpler, between 0 and m, greater than or equal to 0, less than m. But then again, I don't regard this r bar any simpler than this. Let's get this one again. This r bar versus this n bar, in my opinion, they're about the same. Because we are talking about the same equivalence class with just different representatives. It's kind of like this. 4 over 8 is the same as 2 over 4. The same as 1 over 2, kind of like this. Well, okay, 1 over 2 is the simplest, the lowest terms, but depending upon circumstance, the others may be more useful, especially when you have to do some addition with common denominator. Likewise, in this case, you don't really have to go down to r bar. This one is perfectly fine, and if you stick to that, proving that this is a homomorphism is just a one-liner like this. Gamma of n1 plus n2 is n1 plus n2 bar, but that's n1 plus n2 with bars, or n1 plus n2 modulo m. And we established this way back in lesson 1, don't you remember? This one here, the middle part. The addition is well defined with all those equivalence classes and quotient set. We did it in lesson 1. And then we did it for multiplication as well, but we didn't get to use multiplication at all up to now. As soon as we hit the ring theory, we'll use multiplication as well. Anyway, just keeping n-to-n bar, this proof became a lot easier. If you try to follow this, it's true, but what if r1 plus r2 exceed m and you have to use the division algorithm once more? It'll get even more complicated. I don't think that's worth it. Let's keep it simple. Next, 1.4, identity and inverse. Let G and G prime be groups and phi from G to G prime be a homomorphism. Then phi preserves the identity and the inverse. So if phi preserves the group operation, then it must preserve the identity and also the inverse. In other words, E equals C prime, and then the inverse of x must go to inverse of x prime, the phi of x. How do you prove that? Well, let's look at this one first. We have to use the fact that phi preserves the identity. Excuse me. We want to prove that phi preserves the identity, this one, but we have to use the fact that phi preserves the operation, group operation. So how do you write identity using a group operation? Think about that. How do you express the identity using a group operation? E as E times E. If I do that, then this is phi of E times phi of E, right? But then again, what is E times E? E times E is just E. So that's what we have in the end. Let me copy and paste it once more. And then remove the middle part and then look at this. What do you have? Phi of E is phi of E times phi of E. And then if I cross out, then everything is out. So we have to have the identity here. And that identity should be identity in G prime. So we have E prime. And that's equal to phi of E. Yeah, we get what we want using the cancellation rule. Let's elaborate this idea. So, same observation. E is E times E, and then use the fact that phi is a homomorphism, get that, and then cross those out means multiply the inverse elements, and inverse times itself, so that's identity E prime, and then that's identity, so they just go away. So we get E prime equals to phi of E. We get the conclusion. Now, how about the inverse? Well, we have to prove that phi of x inverse is the inverse of phi x. So this is what we want. Times phi of x is E prime. That's what we want. So we have to do something here. Do something, whatever. So that we want to get that. If you do, then we are true, because this one, which I just highlighted in red, times phi of x is the identity. So this red is the inverse of this phi of x blue. So the red is inverse of blue, and that's precisely what we want to prove. So the question is, how do we get this? Colors are now confusing, so let's get back to black. No, excuse me, it's better to do it here. And we have to use the fact that phi is homomorphism, so it preserves the group operation. So can you do this? So this is phi of, oops. So E prime. So we want to get this red times blue is E. That's what we want is to get. In order to prove that, we can manipulate this left-hand side using the fact that phi is a homomorphism. Put these together because it preserves the group operation. And x inverse x is E, so that we have E prime. Yeah, we get what we want. Let's elaborate it like this. The same operation. Phi of x inverse times phi of x is phi of x inverse times x, so that's phi of E, so we get E prime. Yes, phi preserves the identity, we just proved it. And therefore, this is the inverse of phi x. Okay, that proves this property, the homomorphisms, preserves the identity and the inverse. Next, let's go to isomorphisms. Some properties of isomorphism. Well, let's see. Monomorphism, epimorphism, and isomorphism, you know all the terms. Now, here we go. If phi is an isomorphism, then so is phi inverse. The proof is left to the students. Is it that easy? Let's see. So phi inverse A prime B prime is phi inverse of A prime phi inverse of B prime. That's what we have to prove. By the way, phi is sending G to G prime, so phi inverse is going backward. So G prime to G, so primes came inside. So basically, that's what you have to prove, I guess. So that's what you have to fill in. How do you do that? Looks like that's going to be your challenge. Okay, the proof is left to the students. Okay, how about the next part? A homomorphism from G to itself is called an endomorphism. Yeah, all right. An isomorphism from G to itself is called an automorphism. In particular, an automorphism defined by this is called an inner automorphism. The proof is left to the students. Yeah, here's a definition, but is it really an automorphism? Well, it's going from G to G, yes, that's true, but is it an isomorphism, number one? And is it, yeah, okay, so is it an isomorphism from G to G? That's a question. So number one is a homomorphism, preserve the group operations. And then is it a monomorphism? That is it one-to-one? And finally, is it an epimorphism? Is it onto? That's what you have to do. One-to-one, onto, and homomorphism. So those are the three things that you'll have to check. So preserve the group operation. One-to-one. You have to prove these three. Now, if you write those symbolically, most of those will be okay. The onto part may require a bit of a work. Again, the proof is left to the students. The final topic here, let G and G prime be groups. If there exists an isomorphism from G to G prime, then we say G and G prime are isomorphic. Essentially, they're the same, and we denote like this. We can regard it as a group equivalence. What do you mean by equivalence? Equivalence relation. In order to have an equivalence relation, we have to have a certain set, and then we have to consider various subsets there. But then again, set of all groups, that's going to be too big. It's kind of like set of all sets. We do this. Let G be a big group, and let's consider the set of all subgroups there. So S of G. This one does not have any algebraic structure. We just consider all kind of subgroups there. And then we can consider a relation here with a group, a subgroup H is isomorphic to another subgroup H prime. And both are subgroups of capital G, which is really big. And this is an equivalence relation. So you'll have to prove that you have to the properties reflexivity, symmetry, and transitivity. And this proof looks like pretty trivial, but I don't think this is particularly worth it. But the other two are interesting enough, so I'm going to leave you those two problems as homework problems. Okay, that completes section 1, and let's meet again for section 2 in a separate video.